Okay, now let's move on to the next topic, which is planar kinetics, force and acceleration, and now we're talking about rotation. Okay, so let's look at the equation of motion for rotation. So this is a free body diagram of a rotating rigid body. So this rigid body is rotating about point O, and you can see a lot of external forces acting on it. So when you draw a kinetic diagram, you will see that there is an arrow in both tangential and normal axis, as well as there is also rotation component now involved. Okay, so in rotation, we will be using normal and tangential axis. Okay, normal axis is pointing to the center of rotation. Okay, and tangential axis is tangent to the path, tangent to the circular path. All right, so in this case, you will see that the normal axis is pointing to the center of rotation. This is point O, center of rotation, so this is normal. And if you imagine point O rotating, point G rotating about point O, so this will be the circle, the path. So tangential axis is tangent to this path. So this is tangential axis, and normal axis is pointing to the center of rotation O. Okay, and we have also defined defined previously that the normal axis AN is equal to omega square times R, and tangential component AT is alpha times R. This was derived based on the kinematics chapter. And in this chapter, we are not going to calculate moment about G, but we prefer to calculate moment about center of rotation. So it is calculation of moment about O, all right? And this will be equal to IO alpha. So now we have the rotation component. IO is the mass moment of inertia. Okay, please refer to the lecture video on mass moment of inertia. All right, and I will be explaining some of this in the upcoming tutorial question. Okay, let's move on to question number 1. Okay, now there is a disc supported at a pin at A. So this will be center of rotation. All right, if it is released from rest, determine the initial horizontal and vertical components of reaction at the pin. So let's start by defining the coordinate system. So in this case, this will be, so if you imagine this is point G over here, all right, so point G will be having a circular path about point A, okay, and the tangent to this path is here. This will be tangential. That's why we define tangential like this. And the normal axis will be pointing to the center of rotation, which is point A. So this is normal. So that's why we use normal axis like this. Okay. All right. So let's remove all this first and draw the free body diagram. So there will be a weight pointing down at the center of gravity. At at the pin there will be reaction forces, okay, in both normal as well as tangential axis. So these are the forces that we want to determine based on the question. And now the kinetic diagram. So now notice that it says determine the initial horizontal and vertical component. Initial here means that the angular velocity is still equal to 0 because the disk has just been released. So there is still no angular velocity involved. That is what it means by the word initial. So in this case, we're going to have MAGT pointing down. We have IG alpha. Then and there is no component in normal axis because we know that initially point G is not moving to the right. To the left. Point G is not moving to the left initially, so there is no horizontal. There is no component in the normal axis. So when we look at the first equation, sum of Fn equals to MAGN. MAGN is equal to 0. This is equal to 0, so we know that AN equals to 0. Okay, so there is no there is no reaction force in normal axis initially. Okay, now we move on to the tangential component. Sum of Ft equals to M alpha R. All right, so we have minus AT plus the weight. This is the weight over here, and equal to M, which is AT times alpha times R. R here is the radius of the disk, which is 1.5. So we have minus AT minus 120 alpha equals to minus 784.8. So that is one equation. We need another equation to solve the unknowns. We move on to the mg. So now we would like to calculate the moment about G. We can do moment about A as well, but now let's just focus on calculating moment about G. Okay, because we want to know what is the value of AT. If we calculate moment about A, then there is no AT involved. All right. So now note that we need to know what is IG, which is the mass moment of inertia. So there is a set of a table which lists down the formula to calculate the mass moment of inertia for several homogeneous shape. So this is one of the homogeneous shape, which is a disk. So according to this table, thin circular disk, these are the mass moment of inertia formulas based on the axis. So now let's look at which one is suitable for this problem. So this is rotating at, where is the rotation point here? The rotation point here is at this point. Okay, so the disk is rotating about this point here. So basically we are looking at Z prime. So here this will be the correct formula, I Z prime Z prime. I'm sorry, Z prime is when we want to calculate IA, if we want to calculate I at point A. Sorry, now we are focusing on point G, so definitely we have to use Z only. So we refer to IZZ, which is 1 over 2 mr square. So we have 90 kg meter square, that is the unit for mass moment of inertia, Ig. So then we can substitute in here AT times 1.5, okay, because moment about G, mg has no moment about G, AN is equal to 0, so you only have AT going this way, which is clockwise. So from here we set clockwise as positive, so this will be positive. So 80 times 1.5 equals to 90 alpha. Then we can solve these two equations together simultaneously. We will get alpha is 4.36 rad per second square and AT is 261.6 Newton.